Hello. Today we're going to look at molecular orbital theory, a review of 1211. Pretty quick, just going over what exactly molecular orbital theory is and how it looks and how we use it. So molecular orbital theory is a theory we use because the valence bond model really kind of fails to explain how the molecular's excited state is, how it works, how it functions. So molecular orbital theory does a really good job of explaining a molecule's excited state. It is definitely a more sophisticated model, a little bit harder to understand, a little bit more math involved in the making of it, but we're not going to be doing any math, we're just going to be looking at it. We're going to use molecular orbitals instead of the atomic orbitals. Atomic orbitals overlap to give rise to molecular orbitals, where the molecular orbitals describe the entire molecule. Like I said, this is a mathematical operation in order to get to these molecular orbitals, but we will not be doing that. However, we still observe the same rules we do within atomic orbitals. So we still follow Hund's rule and Pauli's exclusion principle. So we're still going to have filling of orbitals that are lower in energy. We're going to put 2 electrons in spin up, spin down in one orbital. And we're going to add electrons in singly in degenerate orbitals before we pair them up to minimize repulsion. The way that molecular orbitals differ from atomic orbitals is one, atomic orbitals only describes atoms. Molecular orbitals, however, describe the entire molecule. So when you have 2 orbitals, 2 atomic orbitals that overlap, you get 2 molecular orbitals. One will be lower in energy, call this our bonding molecular orbital. One will be higher in energy, called the anti-bonding molecular orbital. What it looks like for hydrogen is as such. We have 2 hydrogen molecules that are isolated with their atomic orbitals. We add the wave functions of the orbitals to get our bonding orbital, and then we subtract the wave functions of our atomic orbitals to get our anti-bonding orbitals, so they'll be higher in energy. So we get a wave function that's lower in energy, representing bonding molecular orbitals, one higher in energy that represents the anti-bonding molecular orbitals. The bonding molecular orbitals are going to be constructive combinations of atomic orbitals. So when we think about a wave, when they constructively combine, we get a larger wave, right? So they're almost always going to be lower in energy than the atomic orbitals. There are some cases where this is not true, but you're not going to really see that in this class. And then we have anti-bonding orbitals where we have a destruction combination. So 2 waves that are not in phase with each other, when they are combined, they are going to cancel out, or mostly cancel out, which will mean they'll be higher in energy. So what happens is we actually develop a node. So if you look over here on the right, we see the hydrogen with the electron density between the 2 atomic orbitals, or between the 2 atoms, representing a bonding orbital, while in the anti-bonding we see a node, or a place where there is no electron density between the 2 hydrogen atoms. So that is not very conducive for bonding, so that would be the anti-bonding orbital. So any electrons in that anti-bonding orbital will cause there to be a node between the 2 hydrogen nuclei. So remember, it is an area of 0 electron density when we're talking about a node. Some more terminology that we're going to be looking at. We'll be talking about sigma bonding orbitals. So this is when we're sharing electron density between 2 nuclei. So this will occur from the overlap of 2 s orbitals, an s and a p orbital, or between 2 p orbitals that are on the same internuclear axis. Usually we look at it as px, although sometimes you'll see it as py. I usually refer to it as px. Then we also have a sigma star, so our anti-bonding orbital, so when we have a node between the 2 nuclei. We also have pi and pi star, where pi is an indirect overlap of 2 parallel p orbitals, and pi star is when we add that anti-bonding aspect to it, so then we actually get a node in between them. To determine if or what type of bonds we're going to be forming within a molecule, we can look at the bond order. The greater the bond order, the greater the stabilization between 2 atoms within a bond. If we have a 0 bond order, that means that there is no bond between the 2 atoms. A bond order of 1, we have a single bond. bond order of 2, we have a double bond, bond order of 3, we have a triple bond. We determine our bond order by taking the number of electrons in our bonding orbitals, subtract the number of electrons in our anti-bonding orbitals, and divide the whole thing by 2. We'll look at that in just a minute. So let's look at an example of He2. So helium-2, you may not have ever heard of it, and for a good reason. When we take our orbitals, we take our 2 atomic orbitals, we overlap, we get our bonding orbital and our anti-bonding orbital. We have 4 total electrons, so we're going to add 2 electrons into our bonding orbital and then 2 electrons into our anti-bonding orbital. Okay, so if we take that and we put that into our bond order, we're going to have 2 electrons in our bonding orbital, 2 electrons in our anti-bonding orbital. 2 minus 2 gives us 0, divided by 2, giving us a bond order of 0, which is why you have never heard of He2 or helium-2. You can always use this with any diatomic to determine is there going to be a bond that forms between these two. With helium-2, we know it's not true. Helium-2, 2+, on the other hand, will in fact form a bond or form a molecule because we'll have removed the 2 electrons in our anti-bonding orbital, and its molecular orbital diagram will look just like helium or hydrogen that we saw earlier. We call this a linear combination of atomic orbitals. That's kind of the mathematical term for what's going on when we're forming these molecular orbitals. So when we overlap 2 atomic orbitals to form the molecular orbitals, in MO theory, we add together the wave functions. We either do it where our wave functions are added to give us sigma and pi, or we can subtract the wave functions to give us sigma star and pi star and get our anti-bonding orbitals. But it's a linear combination. If you ever go into PChem, you'll do much more about that, but just knowing that the term linear combination of atomic orbitals is as far as we really need to go with this. With our molecular orbitals, we can have a gap between filled molecular orbitals and unfilled molecular orbitals. We call this our HOMO and LUMO, highest occupied molecular orbital and lowest unoccupied molecular orbital. And this is where we're starting to get into the excited state, using molecular orbital theory to describe the excited state. So we know electrons can only go in orbitals. They cannot go in areas where there are an orbital. So if we don't have energy states or orbitals in a molecule, then we can't excite electrons to that. So if we have electrons in our HOMO, we can excite them into our LUMO orbitals, our LUMO orbital, and that allows us to get that excited state. And then when it relaxes back down, we can get emission of a photon like we saw in 1211. That gap will tell us how much energy is required to excite an electron from our highest occupied molecular orbital to our lowest unoccupied molecular orbital, called the HOMO-LUMO gap. Okay, let's look at a couple of period 2 diatomics, which are from lithium-2 to fluorine-2. So now we're going to include p orbitals. So keep in mind, number of molecular orbitals that are formed will equal the number of atomic orbitals that are used to make these. We have lithium-2 and beryllium-2, the 2 within period 2 that don't actually have p orbitals. Lithium-2, as we can see, should form because we have a bond order that is 1. However, beryllium-2 will not because we have a total bond order of 0. So let's look at how our p orbitals are going to affect our molecular orbital diagram. So first of all, we have 2 types of interactions between p orbitals. We're no longer dealing with a sphere, we are dealing with a dumbbell shape. So we have either end-on or sideways overlap. End-on is right here, sideways is right below. Our end-on, that will give us the sigma and sigma star molecular orbitals. So here's our sigma, where we've got electron density between the nuclei, and sigma star, where we have no electron density between the 2 nuclei, and we form a node. We can also have side-on overlap, so this gives us pi and pi star. Here's our side-on, where we have electron density, no matter what, we're going to still have a node, but, sorry, not this one. Here and here, let me just erase that real quick. Here and here, where we have electron density between our nuclei, and then we have a node forming for our sigma or our pi star. Here is the general form of the molecular orbital diagram for a period 2 diatomic. However, there is some interesting things that go on with our period 2 diatomics. There is going to actually be a more overlap of the orbitals between S and P when we have a lower effective nuclear charge, such as in boron, carbon, and nitrogen. The electrons are further away from the nucleus, so their orbitals are interacting more, and we get a rearrangement of the orbitals for B2, C2, and N2. So this rearrangement that we see here is what is caused by that, and so there will actually be differences in our molecular orbital diagrams between boron, carbon, and nitrogen diatomics versus oxygen, fluorine, and neon diatomics. Again, neon, you see, has a bond order of 0, so it will not form, but it'll look like that. And that is the entire thing. Hope you guys have understood that, and if you have any questions, please let me know.